Welcome. So, we are looking at the diffusion equation and phase field equation. So, let me write them down. So, we are looking at the equation dou C by dou T is equal to m by n v f double prime del squared C by del x squared. So, this is the diffusion equation, and the phase field equation is same dou C by dou T is equal to m by n v f double prime del squared C by del x squared minus 2 kappa del power 4 C by del x power 4. Now, what I want to do is that if I put a sinusoidal variation, what happens to that variation, right? We know that diffusion equation means that sinusoidal variations should become flat, and in the case of spinodal decomposition they should grow, right. So, that is what the meaning of spinodal decomposition. Any small fluctuation you have automatically grows, that is regions rich in A keep becoming richer in A, and regions poorer in A keeps becoming poorer in A. So, that is the solution, which means that compositional heterogeneities tend to grow. Whereas diffusion equation, we have looked at the physical meaning of diffusion equation. The curvature term basically decides whether the composition will grow or decrease or remain constant at that point. So, basically a sinusoidal wave will become flat. So, this we have seen. So, this is the same analysis that we are doing now, but we are doing it a little bit more mathematically. Probably we have done some of it for the diffusion equation. Let us repeat it once more and see in these two cases what the differences are. So, I am going to take C minus C naught to be equal to A of beta t exponential I beta x as the solution in the two cases. So, now what is beta? Beta is nothing but 2 pi by lambda, where lambda is basically the wavelength of the compositional fluctuation that you are putting. So, this is basically the lambda. So, what I am saying is that let me introduce a compositional fluctuation. So, that is what is described by exponential I beta x, and with time. So, the A beta is basically the coefficient. If this A beta is going to grow, then that fluctuation is going to grow, because that is the amplitude of the fluctuation. And when the compositional fluctuation dies down A beta with time, because this is the only time dependent term, this is the only position dependent term, right. So, that is what we are trying to do. So, if we substitute it back here, what do we get? Because dou C by dou T, now this is the only time dependent term. So, this will remain. So, we get dA by dt into exponential I beta x is equal to, now when we do this, A will remain, because that is time dependent, only this term has the position dependence. So, that is 2 I betas will come out, one I beta will come out, another I beta will come out, I squared is minus. So, you will have minus m by n v f double prime beta squared and exponential I beta x, because remember when I differentiate it with respect to x, I get I beta exponential I beta x, and another I beta comes. So, that is what gives minus I squared. So, this 2 goes away. So, this basically means that dA by dt is equal to minus m by n v f double prime beta squared times A. So, this is what, in a similar fashion when I substitute here this expression, okay. So, let me split the paper. So, I am going to get dA by dt to be equal to minus m by n v f double prime beta squared minus 2 kappa beta power 4. Okay. So, all of that then multiplying A. So, if we solve this equation, you know, this is dA by A is equal to this times dt. Similarly, here dA by A is this times dt. So, let me call this quantity as R of beta and this quantity as the R of beta in this case. Then I get the solution. So, this is simple. So, you can do that. You get the solution as A of beta comma t is nothing but A of beta comma 0 exponential or beta t, and in this case also it is the same. A of beta comma t is equal to A of beta comma 0 exponential R of beta t. So, this is the, so depending on R of beta, if it is positive, for example, it is exponential term, so it will keep increasing. So, this is the initial at time t equal to 0, this is the amplitude. That amplitude will keep growing if R is positive, it will decay if R is negative. Similarly, here depending on whether R is positive or negative, this will grow or decay. Now, given that, so let this be the starting point for further analysis. So, let me write down A of beta comma t, that is the amplitude, how is it changing with time of the sinusoidal variation that we have put is nothing but A of beta comma 0. So, the amplitude at times 0 times exponential of R of beta multiplying t. So, with time, if R of beta is positive, this is going to grow, R of beta is negative, this is going to decrease. So, now in the case of diffusion, the classical diffusion, we know that this is m by nv f double prime beta squared, and in the case of Conn-Hilliard equation, it is minus m by nv f double prime beta squared plus 2 kappa beta power 4. Now, let us assume that we are in the spinodal regime. So, in which case f double prime is less than 0, right. So, that is the case when we want to look at these two equations and see what happens. So, when f double prime is less than 0, that is negative, m is a positive quantity, that is mobility, nv is the number of atoms, that is a positive quantity, beta is squared, so that is a positive quantity. So, f double prime being negative means that R of beta is greater than 0. That means for any beta, any wavelength, it does not matter how small the wavelength is or how large the wavelength is, this quantity is going to keep growing with time. So, this quantity, so if you take dA by dt, that will be nothing but R beta, right, R beta times A. So, that R beta is going to be a positive quantity. So, dA by dt is going to be a positive quantity. So, that is what happens in the case of diffusion. On the other hand, if you see this case, so you have R beta. So, let us take here also f double prime is less than 0, in which case you will have, so this quantity, so that will become R of beta is equal to minus m by nv 2 kappa beta power 4 minus mod f double prime beta square, right. So, the negative sign is taken and I have written f double prime as minus mod f double prime. So, this is just a number and the sign is already taken into account. Now, you can see that for small beta, remember beta is 2 pi by lambda. So, smaller beta means larger wavelength. For larger wavelengths, you see that this quantity is going to be dominant than this. For small beta, this is going to be a larger quantity. Of course, it depends on f double prime value and kappa value, but for some f double prime, some kappa, you can always find a beta in such a way that this term is dominant. Then that means this quantity becomes within this bracket is negative. So, that is going to make this R beta to be positive. Okay. So, large small beta, R beta is greater than 0. However, when you go to large beta, that is small wavelengths, when you go large beta, okay, small lambda, when you go to that case, you can see that this term becomes dominant. So, then that this quantity within the square bracket becomes positive. So, that means this becomes negative. So, R beta becomes negative. So, what does this mean? In the case of spinodal decomposition, okay, large wavelengths will grow, but there is a critical wavelength below which, and that is decided by where this quantity becomes 0, right, that will not grow, and below that anything will have negative rate of growth, that means those will decay. So, this is what sets the lower wavelength limit. So, experimentally it was found that when some systems undergo spinodal decomposition, it is found that there is a lower wavelength limit. Many waves higher than say 100 angstroms would grow, but anything less than 100 angstroms would not grow. So, that 100 angstrom, that critical wavelength which will not grow, is basically decided by this quantity, by at what point this becomes 0. Thus, we have from the Kohn-Hilliard equation a solution which automatically makes sure that wavelengths which are larger than a critical wavelength grow, wavelengths which are smaller than any critical wavelength which will die down. Okay. So, thus that R beta term in that sense will actually decide how the terms grow. So, this you can plot, you can, if you plot and see, so you will find that this is how it goes. So, in the case of diffusion, so if you are looking at beta versus R of beta, in this case when R of beta is positive for all beta, it will go like that. But in this case when you have a large beta, when this is negative, so you are going to have a curve which is going to be like that. Okay. Very small beta, so this is positive, so it will grow, and there is a large beta which corresponds to small lambda, that is going to be negative. So, where it becomes 0 will be decided by where this quantity becomes equal to 0. At that point there is no growth rate becomes 0. So, that will neither decay nor grow. So, that is the critical wavelength, and this plot also shows that there is a maximally growing wavelength. So, there is a maximally growing wavelength, there is a critical wavelength. So, any beta which is less than this will not grow, which is greater than this will not grow, which means less than some wavelength will not grow. Any beta smaller than this will grow, which means some large wavelengths. I mean, this 0 basically means because beta is 2 pi by lambda, infinite lambda, so infinite wavelength. So, these are large wavelengths, and you can see why the curve is like this. If the lambda is very large, diffusion has to take place over larger distances. So, even if it grows, the growth rate will be slow, and as the beta becomes larger, when the wavelength becomes smaller, diffusion will be over smaller distances. So, that can happen fast. So, the growth rates will be large, but below a critical wavelength, the interfacial energy contribution is so high that is going to kill the growth of these. So, that is why there is this critical point. So, that is the reason why you get a curve like this. So, this is the classical diffusion equation, this is the Kohn-Hilliard solution. Okay. So, now we want to do all this numerically and try to put, for example, different wavelengths and see what happens and things like that. So, that is what we will do in the next lecture. So, we are going to take the diffusion equation and the Kohn-Hilliard equation. We are going to look at the implementation using finite difference and using Fourier transform, and we will plot these solutions, and we will do all that in one dimension, so that we understand things better, and we will also try to calculate what is the interfacial energy associated with the system and see what happens. So, that will be our next lecture. Okay. Thank you.